So Carl came to Cornell 5 years ago with an undergraduate degree in math from UNC Chapel. He worked for 1 year and then returned to NC State where he took courses in aerospace engineering, got 4.0 GPA. In those courses, gained research experience, including a paper, and applied for the PhD program at Cornell. I saw Cornell, Carl's application in the PhD pool, and I was very, thoughtful about who I was recruiting to build a lab with me. So it's not an accident that Carl got here for me. Like I looked through the pool and I was really excited to see his application. Had no doubts about his ability to succeed. I was really excited that Carl would be able to, hoping he would come here and help me build a lab. So he began to work in Astrolab even before he officially matriculated at Cornell over the summer 2020. He was working on a new simulation tool, which many of you, the lab members in the audience have worked on evolved versions. So you can thank Carl for his initial work on that. We had just developed, that it was just in development in 2020. Fast forward to 2022, Carl was awarded a NASA fellowship for the remainder of his PhD studies. These are very competitive awards, only given to 50 students in the whole country a year. So that was a huge achievement for Carl and for our group to have that kind of recognition. And then through this fellowship, he spent summers at NASA Glenn, which is the birthplace of electric propulsion in the US, and NASA JPL, which is the lead research center that works on this electrospray technology that you can hear about. So he made significant contributions there to the technologies and importantly for us, brought back some techniques and wisdom to Cornell with him. So we've actually been awarded like a new instrumentation grant based on the work that Carl did at Glenn, which I don't know if that's even in your presentation today or not. Either way, it's okay. So as I said, he was Carl's very first PhD student to join our group, and he built our lab, as hopefully he'll show us here, from literally an empty room to a room that's too full now with 3 vacuum chambers and more tools and storage space, but also have helped us manage that and reorganize it this past year. So I just wanted to say that this is so long, but I think neither Carl or I could have predicted in 2020 where like his research project or this brand new lab would go. We knew that there were some really interesting questions. I knew Carl would be able to help me and help us answer those. So I'm very grateful to Carl for taking the chance on me and the research group to be the first PhD student, and you'll get to see today the great work that he's done. Thanks.
Thank you so much. All right. Thank you everybody for coming to see my defense today. Yeah.
I appear to be muted. I don't know if you're recording.
So I'm actually recording the meeting, and I think it's only recording my audio on my computer locally, okay. And so I muted this one, but my audio is good, and I'm assuming people online can hear me fine. Probably. I think they'd say if they couldn't. Yeah. Okay. Great. Yeah. Thanks again, everybody, for coming. Today, I'll be talking to you about my work to develop novel diagnostics for characterization of neutral species in electrospray plumes. So here's an outline of my talk today. First, I'll give a background on electrospray thrusters and give a little bit of motivation for my work. Then I'll talk about early work aimed at characterizing propellant deposition onto substrates. Next, I'll talk about efforts to determine a relationship between the frequency response of a quartz crystal microbalance, or QCM, with the energy of impacting electrospray plumes. And next, I'll talk about my work measuring secondary species as a result of energetic electrospray plume impacts. And then finally, I'll give my recommendations for future work. This is a form of the Tsiolkovsky rocket equation, which describes the amount of propellant that is required for a spacecraft to make a maneuver. These maneuvers could be launching or landing. They could be raising or lowering your orbit. They could also be escaping orbit, which is necessary for interplanetary missions and beyond. Some people in the audience, mostly the people on Zoom, are not going to be as familiar with this equation, so I'm going to go ahead and break it down. This equation is derived from a conservation of momentum argument. Expelling propellant in one direction is going to result in momentum imparted on your spacecraft in the opposite direction. And for this reason, the variables at play are propellant mass, spacecraft mass, the change in velocity of your spacecraft, and the exit velocity of your propellant. We see that a linear increase in a required delta V for emission is going to result in an exponential increase in the propellant that's required. This is going to ultimately limit what missions are going to be capable for certain thruster architectures. This unfortunate fact is what we sometimes affectionately refer to as the tyranny of the rocket equation. So what could we do about this? Well, for a given spacecraft with a given delta V requirement, we only have one variable to play with, and that's the exhaust velocity of the propellant plume. If we have a rise in a delta V requirement for a mission, we could also increase the velocity at which propellant is expelled out of the thruster to offset propellant costs, thus keeping the total needed propellant in check. To compare to something a little bit more familiar to people who've maybe not seen this before, this could sort of be, this is analogous to, say, a road trip in a car. The delta V could be seen as the distance that you're going, and the exhaust velocity could be seen as the efficiency of your vehicle or the miles per gallon for your engine. We don't typically work with exhaust velocity as a metric for thruster performance, though. We usually work in terms of impulse per unit weight of propellant, or specific impulse, or ISP. This is simply the exit velocity divided by the gravitational constant due to, or the acceleration due to Earth's gravity at Earth's surface, G naught. Typically, when people think of rocket propulsion, they usually think of something like the image on the right here. This is NASA's Space Launch System, or SLS, which is capable of delivering very large thrust and power outputs for a very short period of time, only a few minutes before it completely runs out of fuel. The power for this fuel is stored in the propellant itself in the form of chemical bonds that are broken upon ignition. And because of this, the energy of each unit of propellant is ultimately limited. And so we actually get relatively low specific impulses. And for this reason, launch vehicles like the SLS here have to contain notoriously high propellant mass fractions. In fact, this vehicle is approximately 85% propellant by mass. Chemical rockets are currently our only method for producing enough thrust to combat Earth's surface and enter orbit. But once we're in orbit, perhaps there are better options. Electric propulsion is an excellent alternative once we're in orbit, and the forces acting on the spacecraft are either small or balanced. Generally speaking, electric propulsion devices operate by ionizing a propellant and electrostatically accelerating them. Our ability to generate very strong electric fields on board means that these propellant particles can be accelerated to very high velocities, and we can get very high specific impulses. Shown here are a few different electric propulsion devices. On the top left and bottom are both Hall effect thrusters operating on krypton and xenon, respectively, both noble gases. And on the top right here is a gridded ion engine that operates on xenon. I actually took these images myself when I was working at JPL last summer, like Elaine mentioned. I was fortunate enough to see these two Hall effect thrusters firing. And this gridded ion engine shown here was actually an ion source that I used for a series of experiments at NASA Glenn, where I worked at a couple summers ago, rather. Because these systems use non-reactive noble gases as propellant, the power for propulsion needs to come from some external supply. We're going to need a power supply on board, and so the power and thrust that these systems can generate is ultimately limited by that. But generally speaking, limited thrust once you're in orbit with minimal other forces acting on your spacecraft is going to make maneuvers take longer, but not necessarily otherwise limit mission capabilities. Electrospray thrusters are another class of electric propulsion that are capable of delivering high precision nano to micronewton levels of thrust at very high specific impulses. Today, there are two primary flavors of electrosprays. We have liquid metal ion sources called PHEEPs and ionic liquid ion sources. They both operate on the same principle of electrospraying, but they differ in the propellants that are used. PHEEPs use metals that are melted on board, usually indium, and then electrosprayed, while ionic liquid ion sources, as the name suggests, uses ionic liquids as propellant, which are vacuum-stable, room-temperature molten salts comprised of molecular anions and cations. Unlike many traditional electric propulsion devices, these systems do not need pressurized propellant tanks or ionization chambers, which greatly reduces the complexity of these systems. Ionic liquid ion sources have additional benefits over PHEEPs. The propellant is already a liquid, and so no onboard heaters are required. And because the propellant is comprised of anions and cations, electrosprays can uniquely operate in either the positive or negative ion mode, which can mitigate spacecraft charging without the need for an external neutralizer, which is something that virtually all other electric propulsion devices require. These factors make these systems highly scalable and very attractive for small satellite applications. My work is concerned with ionic liquid ion sources, and so that's going to be the focus of the rest of my talk today. So how do they work? Well, these devices are typically comprised of arrays of emitters, typically modularized in tiles or chips, which is an example of which is shown on the left. Each of these modules contains hundreds of emitter arrays, which are each aligned with an aperture and an extracting electrode. I've made an illustration on the right here of just a single emitter electrode pair. In our source, we use solid tungsten emitters, and these are externally wetted with our ionic liquid propellant. When we apply a high electric potential between the emitter and the extractor, the forces from the surface tension in the fluid and the induced electric field balance, and the liquid is pulled towards the tip of the emitter, at which point the liquid snaps into a sharp cone shape called a Taylor cone. And at the tip of this cone, the electric field is further focused and the force eventually surpasses the ionization threshold. And we eject ions from the bulk fluid. These ions are then accelerated through that same electric field to tens of kilometers per second. And by these means, electrospray thrusters are able to directly convert electric potential energy into kinetic energy, producing thrust. This cartoon is a little bit idealized. The real picture is quite a bit more complicated. In reality, a range of species are emitted in the form of small clusters. The prominent species in the plume are pure ions, which we call monomers, ions with a single neutral attached, which we call dimers. These neutrals themselves are anion-cation pairs of the ionic liquid. And finally, single ions with two neutrals attached. We call these trimers. Measurements and modeling shows that a large portion of these species are actually metastable, and they're going to fragment in that acceleration region. A trimer is going to decompose into a dimer, and a dimer into a monomer, leaving behind a neutral at each step. Since the neutrals are not influenced by the electric field, these neutrals are going to tend to move much more slowly and at wider angles. Their trajectory is going to be based on their velocity and location at the time of fragmentation, while the parent ion or cluster is going to continue to be accelerated on, leaving behind that neutral in the plume. This results in a decrease in thruster performance because we're losing propellant without it contributing significantly to the total thrust of the system. Slow-moving neutrals will disproportionately affect the particle density in the plume, and in particular, in this acceleration region, particle collisions could be important for plume development. Neutral-neutral and ion-neutral collisions will result in momentum exchange, and at high relative velocities, these collisions could result in dissociation of the neutral particle, resulting in two charged particles, the opposite of which is going to stream back to the emitter, which harms the performance of the thruster. These ion-neutral interactions have been studied in technologies with more flight heritage, such as the Hall effect thrusters and gridded ion engines that I showed earlier. And actually, these charge exchange collisions are shown to drive the erosion of grid structures through the production of high energy neutrals and low energy ions. Simulations can be a useful tool for understanding plume development, in particular neutral production and propagation. Modeling efforts between our lab and MIT Space Propulsion Lab use state-of-the-art computational techniques, incorporate Coulombic forces between all the charged particles in the plume, and include a fragmentation model for producing neutrals. Though it's worth noting that they don't currently model collisions, but we have other people in the lab working on that now. These simulations are able to track the position and velocity of ions and neutrals in the plume over temporal and spatial domains spanning several orders of magnitude. Here on the left is a snapshot of the last timestamp of one of those simulations. And as Elaine had mentioned earlier, I began my PhD working with this tool to make predictions about the mass flux of neutrals impinging on the extractor electrode, which is plotted over here on the right. And we can see a significant population of neutrals are going to impact the extractor, especially near the periphery of the aperture in the extractor. And these impacts are going to happen at a wide range of energies as well. These models are currently validated through ion measurements of energy and velocity, but this alone cannot fill in the whole picture. It can't be determined if an ion is a product of multiple fragmentation events. For example, if we had a trimer fragment twice quickly in the acceleration region, it could produce a monomer with the same trajectory as a dimer that fragmented once, perhaps a little bit later on. And very rapid fragmentation near the emission site could also result in ions that are accelerated to nearly fully the full plume potential, which would be experimentally indistinguishable from ions that were emitted without any fragmentation events. Both of these processes are going to result in an undercounting of neutrals if we rely on ion current measurements alone, and will result in an overestimate of your thruster performance. So to begin to fully understand the population of neutrals in the plume, improve models, and improve thruster performance estimates, it will be necessary to experimentally characterize neutrals in the electrospray plume. There are significant challenges to experimentally measuring neutrals. First of all, the electrospray plume is extremely sparse, and especially in our single emitter ion sources, this is going to be prohibitive and make direct imaging not possible. Neutrals don't carry a net charge, and so traditional electric propulsion diagnostics, which usually rely on current measurements, are not going to be appropriate. And finally, as I mentioned, the neutrals are going to span a wide energy range, and this means that no single diagnostic may be capable of measuring the range of neutrals that we expect to see. Wide-angle neutrals are very likely to impact critical spacecraft operating surfaces, in particular that extracting electrode. And it's expected that these impacting neutrals are going to interact with surfaces in a manner that is energy dependent, as illustrated on the left. At low energies, neutrals may deposit onto surfaces, leading to thin film buildups. And at higher energies, we might start to see secondary electron emission, cluster dissociation, and surface erosion. And because these are molecular ions, we could even see chemical reactions at these sites as well. All of these processes are going to be destructive to the system and ultimately limit the lifetime of the thrusters that could otherwise be capable of operating for months or even years continuously. The image on the right shows the visual evidence of the negative effects of neutral deposition, or of propellant deposition. This image was taken after about 200 hours of firing, and towards the end of testing, discharge events between the emitters and extractor were observed with increased frequency, which left behind decomposed ionic liquid on the extractor electrode. And in some of these sites, this liquid actually bridged from the extractor to the emitter, resulting in electrical short circuits and failure at these sites, and eventually failure of the entire system. And at this time, it's thought that deposition from low energy neutral overspray may be a lifetime limiting factor for electrospray thrusters. So fortunately for me, I could potentially leverage some of these lifetime limiting processes to actually experimentally detect neutrals in the plume. In particular, I'm going to begin by focusing on low energy particles that I expect to deposit onto surfaces. So a quartz crystal microbalance, or QCM, pictured on the left over there, is a promising tool for measuring propellant deposition. A QCM measures the mass change on the surface of a quartz crystal through the change in frequency of this piezoelectric crystal. As mass is added to the crystal surface, the resonant frequency will decrease linearly, which is sort of similar to how a thicker guitar string, when plucked, may resonate with a lower frequency. The relationship between frequency and mass change is described on the right here by the Sabry equation, where delta F is the change in frequency and delta M is the change in mass, and everything else is a constant of the crystal. It's worth noting that the frequency of a QCM is also dependent on the temperature of the quartz crystal, and so that's why a thermal couple was included to confirm that this thermal drift in our system was actually small enough that for now it could be ignored for our purposes. Based on the parameters of our QCM, a deposition of a single nanogram of material would result in a frequency decrease of 1/20 of a hertz. And because we can measure the frequency change down to hundredths of a hertz, we can actually resolve mass change on the crystal surface down to fractions of a nanogram. QCMs have been used by UCLA to measure the total mass flux of a droplet mode electrospray plume by sweeping the instrument through the extent of this diverging plume. Resulting mass flux profiles are shown on the left, and mass flow measurements through their capillary emitter matched very closely with measured mass flux measurements from the QCM, which indicated that QCMs are a promising instrument for measuring neutral mass deposition. The electrospray source used in this work was a small capillary instead of an externally wetted emitter like we use. And these are known to emit micro droplets instead of individual ions and ion clusters. And it's critical to note that we don't necessarily expect these droplets to interact with surfaces in the same way on impact. For example, these droplets are much larger and they have many degrees of freedom to deform on impact and dissipate their kinetic energy. So even at high energies, these micro droplets could still deposit onto surfaces. Ions and ion clusters don't have this same luxury. And so we don't necessarily expect to see high energy ions, neutrals, and ion clusters depositing onto surfaces. In fact, we may expect them to actually erode the surface instead. To determine if a QCM is going to be a useful tool for measuring mass deposition from neutrals in an ion mode electrospray plume, it'll first be necessary to understand the deposition behavior of these species as a function of energy. Before going into the first set of results, I want to quickly talk about the first ion source that I designed and built in our lab. And this served as the basis for all future iterations, which over the years, there ended up actually being quite a few. This first design was inspired by the ion sources that were used at MIT's Space Propulsion Lab, who we were working very closely with at that time. So there's an aluminum base that has a needle clamp to hold our tungsten emitter in place as it passes through a stainless steel propellant reservoir. The reservoir is held in place in a Teflon block by a threaded rod, and that threaded rod also serves as our high voltage connection. And finally, we have a stainless steel extractor plate up top, and all three of these stages are held off by alumina rod standoffs. This source uses an electrochemically sharpened tungsten needle as an emitter. The tip is wetted with our propellant, EMI BF4, and while firing, more propellant is wicked from the filled reservoir up chemically etched channels through the length of the needle to the tip to allow for extended firing periods without having to break vacuum and reload the source. Deposition of propellant is only expected to occur from sufficiently low energy species. And so this source was equipped with a deceleration electrode so that we could probe reduced energy plumes. To produce a positive ion plume of low energy, we would apply a positive voltage to the emitter and a negative voltage to the extractor such that the electric potential reaches the firing voltage, which is usually on the order of 1 to 2 kilovolts. And finally, the decelerator is held at ground. And because all of our instrumentation and the vacuum chamber itself is also held at ground, the energy of the ions produced are going to be driven by the voltage applied at the emitter. So if we apply only 100 volts at the emitter and extract these ions and then decelerate them with a grounded electrode, the maximum energy of ions in the plume is going to be 100 electron volts. Here's an illustration of the experimental setup in our vacuum chamber to test out the QCM. Since the QCM does not directly measure current, it's going to be necessary to point towards the Faraday cup to determine what current is reaching the crystal surface during each of these tests. This is accomplished with a manual rotatable linear stage. Our mass spectrometer was not yet up and running, and so we couldn't know the emitted species, but literature indicates that externally wetted emitters, like the ones used in this work, typically operate in the pure ion regime. And so it was assumed that we were emitting primarily ions and not droplets. For this experiment, the startup voltage was 2.2 kilovolts, which was used as a baseline to assess the frequency response of the QCM. As the plume energy is reduced, the emitted and collected energies also generally decrease. In fact, the lowest energy that I was able to still get appreciable current from downstream ended up being 100 electron volts. And so this was the lowest energy tested in this work. The current collected downstream by the Faraday cup was relatively low across all tests. This was likely due to imprecise positioning with that manual linear stage. This figure shows the QCM frequency response and the rate at which the frequency changes from plume exposure to a 2200 electron volt plume. There were 2 firing periods. The first was about an hour. The next was about 30 minutes, with 2 off periods, also about 30 minutes each. And while the source is firing towards the QCM, we see a significant frequency increase, which is indicative of a mass removal on the surface. And this supports our hypothesis that high energy particles are not going to deposit, they're actually going to erode the surface instead. This figure shows the QCM response from 3 firing cycles of exposure to a 100 electron volt plume. Because of difficulties maintaining current in this low energy configuration, the firing periods were fairly short, only about 3 minutes each, that were followed by 3-minute off periods as well. It does appear that the frequency is decreasing when it's exposed to the electrospray plume. which would be indicative of deposition onto the crystal, which was promising. But because of these short firing periods, it couldn't quite be determined what the steady state response actually was going to be. And so longer firing periods are going to be necessary. Using the Sawbury equation, the average mass change rate of the quartz crystal was calculated and normalized by the collected current during each test. There's an apparent relationship between the normalized mass change rate and the energy of impacting ions, with greater erosion seen at higher energies. These sizable error bars are primarily driven by fluctuations in emitted currents and short firing periods. Because of these large error bars, it couldn't quite be determined at which energy deposition begins to occur. Further, it was demonstrated that the high energy particles do not deposit onto the surface effectively like they do in the droplet mode electrospray plumes. If deposition is occurring at low energies, simultaneous crystal erosion or film removal could be obscuring these effects. And because of these competing processes, surface characterization techniques will be useful to better understand the state of the crystal surface after plume exposure and determine if there was propellant deposition on the crystal surface. It's expected that the propellant found on any substrate is going to be exceedingly trace. And so we're going to need much longer firing periods than what I've demonstrated so far so that an appreciable layer of propellant can build up. To increase the firing period, I needed to redesign the ion source. The previous source was a little bit challenging to properly align the emitter and extractor between cleaning, which made tests less repeatable. But in this ion source, the primary addition was an XYZ stage that the source is fixed to, which allowed for quick and precise emitter-extractor alignment, drastically cut down on ion source prep time, and it led to more repeatable firing and much longer firing periods, as I'll show you in a moment. This series of tests used quartz crystals as witness surfaces and was focused on post-processing techniques to detect trace quantities of propellant on the surface. 3 samples were analyzed. One was exposed to a high energy plume of 2,700 electron volts. Another was exposed to a lower energy plume of 30 electron volts. And we also have a control crystal that was not exposed to the ion plume at all. Based on firing data, and by assuming equal parts monomer and dimer emission, because at this time the mass spectrometer was not quite yet up and running, we estimated that in the high energy case, over the course of about 17 hours of plume exposure, about 63 micrograms of material impacted the crystal surface. And in the low energy case, after about 4 hours of plume exposure, only about 2 micrograms intercepted the crystal surface. This work explored several surface characterization techniques, but I'm only going to discuss a couple of these today. I do want to quickly draw your attention to an interesting feature that appeared on the high energy crystal after plume exposure. We have 2 distinct regions, one darker crescent region and a lighter gibbous region. Based on line of sight from the emitter through the extracting electrodes, the diameter of the expected exposure area just about matched the approximate diameter of this lighter gibbous region. And so this was taken to be the region where the plume was directly impacting the crystal. With such a clean line between these 2 interfaces, this served as a very interesting spot to focus the first post-processing technique that I'll go over today. So a scanning electron microscope, or SEM, is used to capture micrographs of regions of interest for qualitative characterization. This tool is coupled with energy dispersive X-ray spectroscopy, or EDX, which is used to measure the elemental composition of a surface. For this work, fluorine was taken to be a marker for the propellant because it exists in abundance in the anion and isn't present in any other processes in our lab. Fluorine was found in quite abundant amounts on the dark region, where it was assumed that the plume was not directly impacting the crystal. And we see some propellant on the light region where the plume is directly impacting. And it is true that we don't quite expect to see too much propellant buildup here, because as I've mentioned, we expect to see more erosion than deposition at this high energy regime. However, it was really interesting to see this much propellant buildup on the outskirts outside the exposure region. Perhaps there could have been significant collisionality between particles bouncing off of the crystal after impact with the incoming plume itself. This could result in low energy species covering wider angles and possibly depositing onto the outskirts of the crystal. So this is a more magnified region, image of that same region with the control crystal at the same scale superimposed for reference. So what we see is a bunch of little black dots all over this surface. And fluorine was found in higher concentrations in these regions. And so this was taken to be concentrations of propellant. This further supported that there could be low energy particles depositing at wide angle trajectories. Next, we take a look at the low energy crystal. The first thing you'll notice is the droplets span a wide range of sizes. The diameters span about 3 orders of magnitude. EDX analysis confirmed that these droplets are in fact propellant. But what was interesting in this case was, unlike with the high energy crystal, where there weren't visible droplets, there was actually no fluorine detection. So these appeared to be isolated deposition of propellant. In an effort to determine the limits of detection for EDX, a further magnified region was examined, and we found a very small droplet and attempted EDX analysis. And what we see is the fluorine doesn't even rise above the noise. In fact, I placed this marker here myself for illustrative purposes. The width of the electron beam is about 1 micron. The electron beam used for EDX analysis is about 1 micron. And so it was determined that this was roughly the limits of detection. And so if we have a droplet that is smaller than 1 micron, it may not be possible to actually detect this propellant with EDX analysis. Next, a non-volatile residue test, or NVR, coupled with electrospray ionization mass spectrometry was performed. NVR is commonly used in spacecraft hardware certification and contamination assessments of sensitive surfaces like optics and other sensors on spacecraft. For this test, each sample is rinsed of the contaminants, and the solution is loaded into atmospheric electrospray ionization source and fired down a commercial mass spectrometer. The detection of the positive and negative ions in our propellant was confirmed, shown in the spectrum here on the right. And not only is it possible to determine what contaminants were rinsed off of a surface, but it's also possible to make estimates of the total mass of these contaminants. By capturing a mass spectrum of a solution of known concentration, in this example, it was about 64 micromolar solution of EMI-BF4, we can use the strength of this signal to benchmark against the strength of the signal from the solutions gathered from rinsing the contaminants off of the crystals generated in this study. It's worth noting that this technique is destructive to the samples, of course, because you're rinsing the contaminants of interest off. And so if you were to include it in a line of post-processing diagnostics, this would necessarily be last. The chart on the left shows the approximate mass that was rinsed from the positive or the high energy and low energy crystals. And what we see is about twice as much propellant was found on that high energy crystal when compared to the low energy. But as I mentioned, we saw a much greater mass flux impinging the high energy crystal, about 30 times more actually. And so this implies that this low energy electrospray plume deposits on the crystal surface at about a 15 times greater rate. You'll also notice that there was propellant found on the control crystal. We were surprised to see this. This cross-contamination could have happened in the SEM where they were all imaged together. It could have happened when handling. It could have happened anywhere in between. Frankly, we just don't know. Surface characterization revealed deposition of propellant from both low and high energy plumes, but high energy plumes drive other surface processes that are at odds with this deposition. Perhaps a QCM could still be used for mass flux measurements, but a better understanding of surface mass change as a function of impact energy will first be necessary. In order to better determine how a QCM responds to a variable energy electrospray plume, several improvements were made for the study. A newly designed ion source, which I'll show in a moment, was capable of longer firing periods and included in-vacuum actuation, which allowed for the inclusion of more diagnostics like time of flight mass spectrometry, or TOF-MS, and retarding potential analysis, or RPA. Additionally, a current collecting shutter was included in front of the quartz crystal to more accurately measure the current flux reaching the crystal during each of these tests. And finally, in light of the revelation that SEM EDX analysis may not be the most appropriate for surface characterization of trace propellant, an additional post-processing technique was explored, X-ray photoelectron spectroscopy, or XPS. Here's a CAD mockup of the latest ion source, and it's still the one that I use today. Previously, I relied on a manual linear feed-through to position the ion source, which was not the most precise or repeatable method, and so a more sophisticated setup was required. This one still allows for precise alignment of the emitter and the extractor outside the chamber using the X and Y dials on the linear stage, but now, once we're in the chamber, we actually have control of the Z-axis, the distance between the emitter and the extracting electrodes, which I primarily used to mitigate the negative effects from propellant outgassing when I was pulling vacuum with the loaded ion source, which in one particular summer caused me tons of headaches. So this was a much needed improvement. This could also be used to study how the emission properties change as a function of this emitter extractor distance. Finally, there are two rotational degrees of freedom included, a goniometer, which is seen up top, which controls the pitch of the ion source, and a rotational stage, which controls the yaw and also allows for pointing between different instruments. This allowed for much more precise pointing of our ion source, which was necessary, especially for time-of-flight mass spectrometry, which is notoriously sensitive to ion source pointing. Here's an illustration of the experimental setup. As I mentioned, two more electrospray diagnostics are included. The RPA, which is used for measuring the energy profile and current flux of the ion plume, and time-of-flight mass spectrometry, which measures the ion velocity, which determines the emitted species and the emission mode, as in droplet or ion mode. The startup voltage for this round of testing was 1900 volts, and so this was the highest energy that was tested. The source was capable of producing much higher currents across a wider energy range, and a much larger portion of the current was collected on the downstream electrode in front of the QCM. With this ion source, I was able to achieve a significant current downstream from all the way down to a 30 electron volt plume. And so this ended up being the lowest energy that was tested in this study. And I also included 3 previously tested energies as well. Here's a time-of-flight spectrum from my ion source and its derivative. We see roughly equal parts monomers and dimers with a small trimer population and possibly heavier species. To take a better look at these heavier species, we also capture a time of flight with an extended window, which goes all the way out to about 100,000 Dalton. There does appear to be a contribution of these heavier mass species, possibly up to 10,000 Dalton, but unfortunately, poor resolution from the high mass species make it difficult to assess just how significant this population actually is. The RPA was used to confirm proper plume deceleration, and the 4 curves shown here are each lined up with the intended plume energy. All of the energies probed here had a fairly wide energy range, and this is in part what drives the reduced current that we see from decelerated plumes, because ions with insufficient energy are going to end up being rejected by the decelerating electrode. Here's the frequency response and the calculated mass change from the QCM when exposed to a 1900 electron volt plume. Exposure periods are followed by 5-minute intervals where the QCM shutter is placed in front of the QCM to measure the current flux. Over about 60 minutes, the calculated mass change from this high energy plume exposure was about 1.9 micrograms of removal of material. By integrating the intercepted current at the current collecting shutter in front of the QCM and using the average mass calculated from the time of flight spectrum that I showed you earlier, we estimated the total mass that impacted the crystal surface. And this was about, in this case, 400 nanograms of material, or excuse me, 400 nanograms of propellant. Next, we have the frequency response for a 30 electron volt plume and the associated calculated mass change. Here we have a very clear frequency decrease indicating deposition of material on the crystal surface. In this test, over about 40 minutes, about 40 nanograms of material was deposited onto the crystal surface. And again, based on estimates of propellant reaching the QCM based on current flux estimate, or based on current flux measurements and mass estimates from the time of flight data. We found there was actually only about 27 nanograms of material predicted to have impacted this crystal, which was surprising because that's only 60% of the apparent deposited material on the crystal surface. This could be explained due to the fairly low resolution of the high mass particles in the time of flight spectrum, like I mentioned earlier. This could result in actually an underestimate of the material that was actually reaching the quartz crystal surface. Here are the QCM responses from the 3 intermediate energies tested. In each case, we see an increase in frequency, indicating mass removal at each of these energies. We also see a pretty significant startup period when the shutter is removed from in front of the QCM. And then we see a decrease in frequency, indicating an increase in surface mass when the shutter is placed in front of the QCM. This could be from ambient particles in the chamber depositing onto the surface. And then when the shutter is removed and the ion plume is exposed again, this material that deposited may be more readily removed from the surface, resulting in a steeper decrease in surface mass, which eventually settles into a steady state. And the time it takes to reach steady state was longer for lower energy plumes, which actually ended up contributing to sizable errors at these lower energies. The average steady state mass change rate normalized by the incident ion current was calculated for each plume energy. And since the current collected and frequency response of the QCM could not be taken simultaneously, these values are normalized by the measured current flux from that shutter once again. We see a clear trend at higher energies. These plumes will drive more mass removal. And the numerous improvements to the data collection ended up tightening these error bars significantly, but still the variations in collected current that were exacerbated by low current flux reaching the crystal at low energies drove these still significant variations in calculated average mass change rate at the crystal surface. But as I showed earlier, we did clearly see deposition from the 30 electron volt plume, which is encouraging for using this tool for low energy neutral deposition. X-ray photoelectron spectroscopy, or XPS, was used to measure the composition of the surface of the quartz crystal. Once again, fluorine is taken to be a marker for the propellant. The relative deposition efficiency can be estimated by comparing the atomic percent of fluorine found using XPS with the total number of incident ions on the crystal surface. The deposition efficiency, or relative abundance of fluorine per incident ion, is shown in this figure. And once again, we have significant error bars driven by the reduced number of incident ions on the crystal surface because it is necessarily scaled by that. But we do still see a very clear trend. At high energies, there is significantly less deposition, and at lower energies, the deposition rates increase. Because of this significant reduction in deposition at the higher energies, other methods for detecting higher energy particles are likely to be necessary. I showed this chart earlier to illustrate the effects of impacting particles as a function of impact energy. I've shown that a QCM can detect deposition of low energy species, and I've shown increased deposition rates at lower energies. But what about the higher end of the neutral energy spectrum? I'm going to continue to leverage these problematic surface effects, but instead of measuring deposition, I'm going to measure secondary species production. To give you roughly a sense of the band of neutrals that this study would target, here's a time of flight spectrum that highlights the primary dimer and trimer lines, which will produce fairly high energy neutrals. And the neutrals represented here actually outweigh the entire monomer plume in this particular ion plume. So this is a very significant population of neutrals. UIUC investigated secondary yields from an electrospray source firing EMI-BF4 using a tungsten emitter, presumably operating in the pure ion regime. This group measured yield impacts on various surfaces and found much higher yields at much lower energies compared to atomic ion plumes. Even at the lowest energy tested, 1.5 kiloelectron volts, there was still a very significant population of secondary species. So why might a molecular ion plume more readily produce secondary species on impacts compared to an atomic ion plume? Well, here are some of the processes at play in high energy impacts. Secondary electrons could be ejected from the substrate. We could have sputter products from the substrate itself. But what sets molecular ions and clusters apart from atomic ions is the possibility of covalent and ionic dissociation, which leads to secondary products of the propellant species itself. Covalent dissociation would happen at fairly low energies, and ionic dissociation would happen at even lower energies. It's very likely that particles that do not deposit onto the surface are going to drive some form of secondary species emission. Here's an illustration of the experimental setup for this work. I have a secondary suppression target, which is seen up at the top, which I'll talk a little bit more about in a moment. And in this work, time of flight is used to confirm ion mode emission and once again confirm proper plume deceleration. On the left, we have our target. If we were to have secondary species ejected from high energy impacts, a negative suppression potential will cause negative secondary species to be redirected back onto the target, and positive secondary species will be accelerated away from the target. Those positive secondaries leaving will contribute a negative current read at the target. And if we switch the suppression potential to positive, we see the opposite story. Positive secondaries are now redirected back onto the target, while negative secondaries are accelerated away. And these negative secondaries are going to contribute a positive current to the target. And so if we sweep the suppression potential from minus 100 volts to positive 100 volts, we're going to see a sharp rise in current as the negative ions are beginning to be accelerated away and the positives are beginning to be suppressed at the target. So here's a secondary species curve that I took from a positive plume at 100 electron volts. This curve is clearly a little bit more complicated than the one that I just showed you. The current contributions could come from 4 different species: incoming positive and negative species, and secondary positive and negative species. Incoming positive and negative species are going to contribute positive and negative currents, which is pretty straightforward. But as I mentioned, positive secondaries leaving the target will contribute a negative current, while negative secondaries leaving the target will contribute a positive current. And if we look in the negative region of the suppression potential, we would expect that the population of incoming positive species would remain fairly constant, meaning this current contribution would not change. And it's expected that all positive secondaries will be accelerated away from the target when we have a negative suppression potential. However, it is possible that as the suppression potential goes from negative 100 to 0, we would have an increase in incoming negative particles. This is because lower energy negative ions could be deflected away from that suppression grid. And in this region, of course, we expect to see negative secondary particles begin to escape the target as the suppression potential approaches 0. And in this positive suppression region, we kind of have, again, the opposite story. We would expect incoming negative species to not be affected. At this point, all negative secondary species should already be accelerated away from the target. So this, once again, will be constant. So the contributing factors to these changes in current will be a possible decrease in incoming positive species, but more importantly, the beginning of suppression of these positive secondary species. So if we look at this region here where we have a decrease in current from minus 100 to minus 50 volts, based on the assumptions that I've outlined in this table, a decrease in current would only occur if there's a decrease in ejected positive secondaries, which I expect to be constant in this range, or if there is a decrease in incoming negative species, or excuse me, an increase in incoming negative species. So this region is taken to be the suppression of negative primary species. In particular, this is likely electrons, because these low mass charges are going to be more readily deflected by this negative suppression potential. Using the same logic, this rise in current here represents the negative secondary species beginning to be accelerated away from the target as the suppression potential approaches 0. And this region here will represent positive secondary species beginning to be suppressed, held back at the target. So I did collect data using that probe from a range of plume energies, but I'm only going to show you a few curves today. So first, the highest energy that was tested in this work was 1800 electron volts. And so a secondary species curve from both a positive and negative plume were collected. And in the negative mode, we see pretty much just negative secondary in the positive mode, we see pretty much just negative secondary species. And in the negative mode, we see a population of negative and positive secondary species being emitted. So this may indicate that negative ions have a higher proclivity towards ejecting positive secondary species from a substrate. Next, I fully suppressed the ion plume with the intention of only passing neutrals onto the target. And we see kind of a change in behavior here. There's an apparent rise in the positive secondary species that are produced from the fully suppressed positive plume, with the simultaneous disappearance of these positive secondaries from the fully suppressed negative plume. And if you're looking pretty carefully, you'll see that from the positive fully suppressed plume, there's actually a negative current being read at the target through the majority of that potential sweep. And in the negative suppressed plume, we actually have a positive current seen through the majority of that potential sweep. So something appears to be amiss here. This was an animation made by my lab mate, Adler Smith, representing a rough model of my deceleration scheme. We see a significant population that streams back to the extractor and emitter when the plume is greatly decelerated. Particles with insufficient energy are going to be rejected by the deceleration electrode and accelerated towards the extractor and emitter. And perhaps these high energy impacts could result in their own form of secondary species emission. And in this case, if we have oppositely charged secondary species, these are going to be accelerated in the deceleration region, causing them to mix with our ion plume. Because decelerating the plumes more and more results in greater and greater impact energies at the extractor from these rejected ions, we expect this issue to be most prevalent in highly decelerated plumes and fully suppressed plumes. To confirm this hypothesis, I searched for these unintended secondaries using our mass spectrometer. Spectrums were required for plumes in order of decreasing primary plume energy or equivalently increasing extractor impact energy. First, we have an extractor potential of 2.2 kilovolts, and we see a pretty significant signal at low mass, likely electrons, possibly some hydrogen contribution. As the plume is decelerated, we see an additional secondary species population pop up. And as we further decelerate the plume, we see a greater intensity of these additional secondary species. My co-author on this work, Juliana Hoffheinz, identified the likely species in this mass spectrum. She found many of these same species in her secondary ion mass spectrometry work, which was conducted in the same vacuum chamber, not at the same time, of course, but in the same environment. All of these products are contained within either the anion or cation of the propellant, so perhaps they could be propellant breakup products, but they could also just as easily be contaminants from the vacuum chamber depositing onto these surfaces that are then eroded away when we have energetic impacts on these surfaces. So those unintended secondary species are going to need to be removed from the plume if I want to probe just neutrals. So to accomplish this, I introduce another electrode stack in front of the source to filter out these unintended secondaries. Finally, a fully suppressed positive ion plume with the negative secondaries filtered out is directed towards the target. Current readings at the target are significantly diminished. This is because of the removal of charged species produced from the electrospray plume impacting the target. So the current that is represented here could be taken to be secondaries that are produced from these impacts. Using this assumption, this chart shows roughly equal parts negative and positive secondary species at about 200 picoamps each. And as it turns out, ionic dissociation of a neutral particle is going to result in one negative and one positive secondary product, indicating that this could be the driving process behind the secondaries we see here. This work demonstrated a promising method for detecting neutrals in an electrospray plume. In particular, this could be useful for detecting higher energy neutrals that don't deposit onto substrates. So next, I want to quickly talk about some recommendations I have for future work. So first, I would recommend, instead of using a QCM like we did in our work, I would actually recommend using a temperature-controlled QCM or TQCM, which is pictured here. These have several advantages over standard QCMs. As the name suggests, they can hold the temperature of the crystal surface steady, which can completely eliminate the error associated with thermal drift, which was not terribly significant in our setup. But as we increase testing times and perhaps also increase mass flux, this could end up being an important contributing factor. These tools also typically include an additional reference crystal, which is obscured from the vacuum environment. And so instead of measuring the frequency change, the raw frequency change from the exposed crystal, instead the difference between the reference and the exposed crystal is measured, which is sometimes called the beat frequency. Both of these improvements will lead to a more stable and more accurate mass flux measurements. Also, the ability to control the surface of the crystal is very useful because the condensable ionic liquid is expected to more readily deposit onto colder surfaces. And so if we hold the temperature of the quartz crystal very near the minimum range, we may see a greater deposition efficiency. Also, I just demonstrated the issue with my deceleration scheme. And so instead of filtering out ions and controlling the energy at the ion source itself, for future experiments, I would recommend actually using electrode stacks at the instrument instead, where the ion plume is going to be much less dense. And finally, actually calculating secondary species yields is going to require stable currents at the extent of the positive and negative potential sweep for a secondary species probe. The probe that I designed was intended to have a fairly large collection area and used a biased grid instead of a biased target so that the energy of the ions would be maintained on impact. However, this led to kind of unsteady current readings at the extent of those potential sweeps. And so I would recommend using a different design like the one pictured here, which uses a small grounded aperture in front of the target and biases the target instead. This would result in more stable currents at the extent of that potential sweep at the expense of significantly reduced collection area. This work would also greatly benefit from a QCM frequency responses probed with a very dense energy survey. And as I showed, each of these data points are going to take some time to reach steady state, which will take longer for lower mass flux and lower energy plumes. This could result in excessively long testing times, which our single tungsten emitter ion sources have not yet been demonstrated to be capable of. And so I would actually recommend instead using a full electrospray thruster array, like the one that is pictured here. This would yield higher currents, could reduce collection times, and would result in more steady and longer firing periods. Next, so early electrospray thruster testing revealed inconsistencies with ground testing. And this was later attributed to secondary products that were produced from high energy impacts on vacuum chamber surfaces. This revelation led to the development of a novel beam target by NASA's Jet Propulsion Lab. This is designed to mitigate the effect of secondary species returning back to your thruster. And so with the incorporation of a full electrospray thruster in this work, it would be necessary to include a sophisticated beam target like the one shown here. Also, with the inclusion of a full thruster, we'll be expelling enough mass and propellant to be able to actually resolve this mass change by an analytical balance. This would give us actual insight into the total mass flux expelled during a testing period, which could be used to benchmark the results from other unique diagnostics that are downstream. And I would also recommend including a new diagnostic, a bolometer, which is used to measure heat exchange on impact. These are sensitive to all forms of energy and have actually more recently been used as particle detectors, so they could be promising for detecting neutral species. And in fact, a specially designed bolometer could be capable of measuring the average energy of neutral species as well as the total energy flux. Here's an illustration of this proposed experiment. An electrospray thruster designed by the Air Force, which is used for laboratory use, called the AFET-2, would be ideal for this work. The diagnostic suite would be placed on a rotatable mount so that angularly resolved measurements of the plume can be taken. This work would measure key dynamic surface processes such as heat exchange, erosion, deposition, and secondary species production, which would simultaneously aid in characterizing the neutral population and telling us what the potentially damaging consequences of these particles impacting key operating surfaces could be, which would better inform thruster integration practices on spacecraft. And because each of these probes are going to be looking at the neutral species, they'll necessarily be equipped with their own electrode stack to eject ions. And this should be designed such that there's minimum impact from other neutral and charged species in the electrospray plume, or in the vacuum chamber environment, rather. I'm very excited to say that I've been invited to join the Naval Research Lab as a postdoc to actually conduct these experiments and improve on what I've started here at Cornell. I wanted to kind of take a quick trip down memory lane with you guys, if you'll bear with me. This was an image that was taken just in my second semester. Elaine took this image just before really anybody got in the lab. As Elaine's first student, it was my privilege to see just how much the lab has changed in the short time that I've been here. We had basically nothing in the lab at first. We just had a sad chamber, didn't have all its ports on even. Nobody had tried to pull vacuum on it in years. I think maybe we had a box of wires in the lab at this point. But then just 2 short years later, I took this right before my A exam, and the lab got a lot busier. Some would say it got a lot messier, but this is okay because it means that people are doing work in the lab. At this point, we've collected a few publications and a few more vacuum chambers. And then I took this image just a few more days ago. It's a little bit more organized, which a lot of people appreciated. We moved the vacuum chambers down into the middle of the lab, so that's a lot easier to work on. I'm only a little bit bitter that we waited until just before I'm leaving to make this change. But I know that all the other experimentalists really appreciate it, and future students will also really benefit from this. Here are the publications that I contributed to that I showed in this presentation, and other references that we're talking about in this work. Thank you guys so much for coming, all of you, and everybody on Zoom. Thanks to my family. I think a lot of you are on Zoom right now. Thanks to Jordan, my fiance. I couldn't have done this without you. And thank you, Elaine. You've been a really incredible advisor, and I couldn't have asked for a better experience here. So thank you for taking a chance on me 5 years ago. Thank you guys so much. Oh, and this work was supported by a NASA Space Technology Graduate Research Opportunity. I think I'm required to say that. So thank you, NASA, as well. Thank you.